Okay, welcome to our tutorial session, and it's going to be about your first assignment, which is the use of Octave software to work with crypto problems. And particularly, we're going to deal with a crypto system called Caesar. It's quite trivial, and nobody's using in the serious application this cipher nowadays. But the purpose of this tutorial is for you to become familiar with a tool called Octave. And if you haven't heard of this tool, it is an open source replacement of another very famous tool called MATLAB. Replacement of another very famous tool called MATLAB. Okay, for some reason I'm hearing echo. So the way how it works is it. So the way how it works. Okay, let me. I'm trying to figure out why can I hear the echo. Trying to figure out why can I hear the echo. Okay. Okay, let's just continue. So MATLAB, or I'm sorry, Octave can be installed on your own computer. Okay, I hope it's gonna be better. It can be installed on your own computer, or you can use a resource of you can have it installed. You can use it from our server, and our server is called LTSP. I believe you all had experience in Unix course. If not, I can share with you some instructions of how you can get into this software. But pretty much, let me just continue assuming that you know how to access Octave, and then I will help you to get started on your own. So I'm currently working in the terminal, and Octave actually has a graphical user interface that we're not going to use, because the only thing we need to use today is the command line. So I'm currently working on a server called LTSP. It is actually our classroom server, which is running in room 214. And anytime you are around the campus, you can just sit there in this classroom. But it also can be accessed from the internet. The full address that you want to use would be ltspjswcm.net. And if you worked, if you attended a Unix course this spring or previous springs, you can just use PuTTY or any other SSH client and specify this address as the host name. And then you will get to the server same way as you previously did in Unix course, and then you will be from this exact same place that I'm getting started right now. So to start Octave, you just want to type in Octave and wait a moment to make sure it is started. So Octave gives you a prompt, and the prompt has to be read as follows. This line number 1 actually shows how many commands you previously issued, and it actually shows you index of the current command. So for example, before I give any command and I'm just hitting enter, this index is not getting changed. But for example, if I just type a number 5, number is considered as a command, and command that is about to return a result of command execution. So obviously command of result of execution of command 5 is 5, but what we also can observe that index of command was increased by 1, and this will happen with any other meaningful command. That's one thing. In Octave, you actually can do basic math manipulations and, of course, advanced math manipulations. In terms of basic math manipulations, you can just do something like 6 plus 4. You can use up or down arrow keys to browse the history. You can use left or right key movement keys to move your cursor. You can insert spaces, and spaces will be ignored. Now, you can actually do something more interesting using the brackets, many other things. And if at some moment you will need to raise a number into power of another number, then you want to use head operation. So this head that you can type in with the shift 6, that's the symbol for the power operation. In other words, 5 raised to the power of 3, that's the notation. Now, Octave can deal with variables, and we're going to deal with them a lot. So to introduce a variable, you just type in variable name and a value separated with the equal sign. So a equal to 5 creates a new variable, and this variable is getting assigned with the value 5. Anytime you can just issue command a, and since a was introduced as a variable, it will be recognized as a variable holding some value, and this value will be reported. You can introduce a variable of numerical types and some other types, and by other type I'm mainly assuming a textual data type. So it is not a string, it is not something that you probably used to deal in C# programming, or some of you dealt with this type of things in Java programming. So it is not a classical string, nor it is a legacy character data type. It is something in between. But the easiest way to deal with strings in Octave would be to use quotation marks to surround some text. So I just created a variable C. I assigned it a value of hello world, and this hello world is now stored in a variable. So currently I have two variables, A and C, and both of them have different types. There is one command that you might need to remember very well. It allows you to examine a list of all variables that are currently defined in your workspace. A workspace is a memory that is associated with the current session of Octave. And next time you will restart Octave, those variables will be gone. So they are here as long as your Octave session is active. If you quit Octave, then you lose those variables from the memory. So be careful. And when I type command whos, I'm just throwing variable names along with their data type. So variable A is a variable of type double, and it occupies 8 bytes in the memory. Variable C is a variable of class character. It occupies 11 bytes. Why, for example, double occupies 11 bytes, that's a whole different story, but it is classical interpretation of double precision floating point data type. For the character data type, it depends on how many characters are there in the text, in the textual string. In our case, hello world contains 11 characters. That's why it shows 11 bytes. The variable called ans is already there. It's always there. It gets the value of the previously executed operation. So, for example, I can retrieve variable answer, and I'm getting the last assignment of the answer. So last assignment was here, 5 raised to the power of 3. That's the time when answer was assigned. In other words, answer is being assigned with the last operation that was not stored in a variable. So in other words, when, for example, I execute a command like 66, I do not assign result of command execution into a variable. That's why result is automatically assigned to a variable answer. But if I do something like b equal to 66, then result of command execution 66 is stored in the variable b, and variable answer is not affected. So I can do this, for example, by changing b equals to 70, and in this case, variable b will hold value of 70, and variable answer still maintains the value of 66. So in other words, answer is the last unstored, explicitly unstored result of the previous one of the previous operations. So you probably can ignore it for a while, but one day you will find out that, okay, there was an operation that you forgot to properly handle. You forgot to store result of this operation in a variable, and answer variable will be there for your help. Okay, let us talk a bit more about character data type. As I mentioned earlier, it is something in between a legacy character data type that you can see in many programming languages like C, C++, even Java and C#, and an advanced string data type that is seen in high-level programming languages. Why is this? Because actually this is nothing more but array of characters. And since it is an array, I can always extract, sorry, I always forgetting this syntax. So to access particular entry in the array, you want to use parentheses and specify index of an entry in that array. Indices in Octave's array start from 1, not from 0, as in C, C#, Java. So that's very important. When we'll be working with Octave scripts, you will need to make certain arrangements to actually respect this rule. But as of now, what we can see that C of 1 is H because it is the very first letter in the phrase hello world, and it is here. We also can, of course, retrieve the fourth letter, etc., etc. Indices in Octave can also be used in a bit more advanced manner. For example, what if I need the last letter in the hello world phrase? I know that the last letter would have index of 11, right? So it's character D. But even without calculating this number 11, I can reference it. To do this, you will just need to use the keyword AND. So AND is the last index of an array. No matter how many entries your array has, AND will always point to the last index. And actually, you can use it as a normal variable. So for example, AND -1 will point to the previous to the last entry. and -2 previous to the previous, etc., etc. You can also, as an index, you can use an array itself. So, for example, if I define a variable index and I store the following entries, 1, 3, 7. This way, I defined array called index. It is array of type double, and in this array, I store 3 values, 1, 3, and 7. And I can use this array of indices as index in array C. So in other words, for indexing purposes, I will use array. The way how it works is illustrated below. So C of index will return those letters that are pointed by particular indices, 1, 3, and 7. Obviously, the first one is H, the third one is L, and W is the 7th. Okay, and we also can create array of indices not specifically as array with given entries, but as a range of numbers. So, for example, we know that length of C is 11, and length, that's another operation that you want to remember. It allows you to identify length of something, not necessarily array. Actually, in Octave, pretty much everything is array. Even a single value variable a is an array of dimension 1 on 1. So if we, for example, do length of a, it's going to be just 1, because a is also an array. So length of C is a length of array C. In other words, it shows how many letters are there in this array. And if we want to use this value to actually create an index, another form of index, we can just write something similar to 1 to length of C. So it will give me numbers from 1 to 11 with the step of 1. And if I use this as index of C, of course I'm going to get all the entries in all the letters from the array stored in variable C. Now, let us do it a bit more interesting. Let us redefine index to introduce a step. A step in this syntax would be the second argument, the second actually token, and all tokens are separated with the columns. So this phrase simply means everything starting from index 1 with the step of 2 all the way to 11, which is evaluated from length of C. So those indices will be 1, 3, 5, 7, 11, and if I do it C of index, it's gonna be reduced in length. So I'm just getting all odd characters of the hello world. Now, there is no need for me to start from 1. I can, for example, start from 3. In this case, I will just skip 1 and I will start from 3, and obviously C of index will be this. Instead of length of C, I actually can use end. The only problem with end in this context is that here, when I try to store generated array in the variable, it has no reference to the array C that I will be use for referencing. So I cannot just assign index from 3 with step of 2 to end, because Octave doesn't know which array I will be using this index for. But if I do something like this is going to work without any issues. So I just used index in place. Instead of using the variable index, I use that generated index here in parentheses, and in this context is the same as length of C. And all manipulations with and will work in exact same way as we used to previously notice. So and minus 3 just limits the ending index in this array. Okay. Any questions? Good. So let me now play with a two-dimensional array. A two-dimensional array is an extension of a single-dimensional array, and in Octave, as I said, everything's are arrays, and there is no big difference between a single-dimensional array and two-dimensional array. The way how you define a two-dimensional array is by listing particular entries, and you separate lines in a two-dimensional array with a semicolon if you just create one single string, one single command. So for example, this notation where entries of the same row are separated with space or bunch of spaces, but rows are separated with a semicolon, creates a two-dimensional array. And for the two-dimensional array, you can always operate with the length. So now it gives me length of 3, and that's tricky, because normally we would say that a length of a two-dimensional array, by normally I'm mainly referring programming languages like Java and C#, where length operation first looks at the rows as the primary index and then columns as the secondary index. In Octave, it is all the way around. So 3 is how many columns a two-dimensional array has. And if I need the next index, which is actually the next length, in other words, number of rows, I cannot use length right away. For this purpose, I want to use a function called size. So size gives me two numbers, number of rows and number of columns. And what do you think, what kind of data type returned by size? It is array. So for example, I can assign S assign to S result of execution of command size of A. And now S of 1 will give me 2, and S of 2 will give me 3. So this is just a number of remarks that you probably want to use later on. I'm not saying that you will need to use two-dimensional arrays to deal with the first assignment, but just have this in mind, because one day under some circumstances it will just click in your mind that, okay, this problem is better to be solved with two-dimensional arrays. So that's how you deal with them. Okay, and of course, when we deal with two-dimensional arrays, we need actually to use two indexes. And previously, we would say just one number to be an index. Since it is two-dimensional array, you want to use two numbers, and those are separated with a space. What will it be if I just provide a single index as a reference of a two-dimensional array? I would say it is unpredictable result. Not unpredictable from the standpoint of a typical MATLAB or Octave user, because it is very predictable in this case. But if you just want to play with this, you probably can see that what Octave is trying to do, it tries to represent a two-dimensional array into a single-dimensional array. And the way it does it, it tries to form 6 entries single-dimensional array that can be considered as 3, 2, 5, 4, 7, 6. That's the way it works. That's why a of 2 was equal to 2. A of 3 is equal to 5. And then if we, for example, do a of 5, it's going to be 7. Oh, once again, the order of entries in this case will be 3, 2, 5, 4, 7, 6. Now, for some operations, you might need to reshape a two-dimensional array. And reshape is a function that we can use. So when I executed reshape function without any arguments, it just recognized that, okay, I cannot call this because I didn't specify any parameters. And it gives me a built-in help information. And this same built-in help information can be retrieved by a help command. That's a very important command that you have to have in mind, because sometimes you simply don't know how a particular command works, and you just give help space and then command name. The only difference between the previous output when I executed shape without command, without arguments, and it gave me just this number of lines, the highlighted number of lines, with the output of help reshape, that it gives me all before, everything that I've seen before, and something more. So it is more detailed documentation, and it just gives you more details of how reshape can work. And the way how pagination works, so it's a long document, and pagination is the way how you can access particular pages. If you recall from the Linux course, we have commands like more, less to scroll the pages. So it's pretty much the same. You can use exact same techniques to scroll the documentation if it doesn't fit one single page, but it's not actually part of Octave. It is more as part of the underlying operating system. And very important note that Octave is a cross-platform software. I'm currently running this on LTSP server, which is a Linux server. That's why it uses mechanisms to access particular parts of the content in a native way, which is known in Linux operating system. You can install Octave on Windows, and will likely it will work in a bit different way. So that's why I'm not specifically saying that you can scroll the output of a long documentation in a certain way, because I wouldn't like to confuse you. When you will try to install Octave on Windows, it will work in a bit different way than on our OTSP server. So talking about reshape, I can just probably illustrate it. Reshape, and then according to the typical use, it is A, our main matrix A, and then a number of indexes. So for example, if I just provide 2 indexes, M and N, they will be used as preferred dimension. So let me reshape my variable A in 6 entries in first dimension and 1 entry in the second dimension. In this case, I'm getting the row, and as I mentioned before, actually not row, but the column, because there will be 6 entries in the first dimension and 1 entry in the second dimension. So 3, 2, 5, 7, 4, 7, 6, 3, 2, 5, 4, 7, 6. That's the way it is listed. I can also reshape it in a line-based notation. In this case, it will be one row and 6 columns, 3, 2, 5, 4, 7, 6. Or I can shape it as 2, 3. This way, it is exactly as we had before, and 3, 2 will give me 3, 2, 5, which is a bit strange because it doesn't fit, probably doesn't fit our expectation. I would expect this result of this reshaping would be just a transported version of this matrix. If you're familiar with basic matrix operations, there is one called transporting. And transporting operation, it is a rotation of a matrix around a main diagonal. So compare original matrix A, which is this, with a result of its transposition, which can be executed by A apostrophe. And those entries that were located along the row, they are now located along the column. Those that were previously located along the column are now located along the row. That's the main result of transportation. So, as I mentioned a bit earlier, two-dimensional arrays are good, and Octave is especially good in this type of matrix operations. It has many functions to deal with matrices, but we're not going to use them a lot now for the first assignment. We will touch them a bit more for the second assignment, but for the first, I just want you to be familiar with the idea that Octave is good with matrices. So let me now jump to the part of Octave functionality that can be helpful for our application. And our application is a Caesar cipher breaking, and it actually manipulates with text lines, with the pieces of text stored in variables. The way it works is illustrated in a script, Octave script file that you can download from the assignment statement, because I gave a file called caesar.m as attachment to the assignment. And that file you can load into your Octave session. And let me illustrate you how you can do this, because in this case you can start from seeing how a particular Octave script can help you to deal with a problem. So let me first quit my Octave session, and it could be either command exit, or you can, if you work on Octave running in Linux, you can just hit Control D. Now, since I'm working on LTSP server, I expect you may work on LTSP server as well. You can access that file Caesar that I preliminarily stored in M directory. So file Caesar is stored there, and what you can do, you can just copy it from there to your home directory. Once you copied it here into your home directory, you will have it, and now you can use it in Octave. So I'm going to restart Octave. First of all, I want to make sure that the file that I want to load into Octave is located in the directory where I'm starting Octave from. So Caesar.m I put into my home directory because I was located in the home directory. And I'm starting Octave. Not listen. In my home directory. So just to make sure that file Caesar is available directly from Octave, I can give command ls. So ls command given in the Octave will do pretty much the same as ls command executed in the shell, and I can see that Caesar.m is here. So now I can load Caesar, and to load the script, I need to type its name, just Caesar, without an extension .m. So just name Caesar. How do I know that the script was loaded? First of all, the main attribute of the successful load is the absence of any error messages. If my script contained an error, then there would be error message, and in other words, it wouldn't be loaded. We're not currently discussing what is there in the Caesar. Of course, you can open it in the editor. Let me just do the trick and show the way how it works, because it's also part of your assignment. So first of all, I want to examine what kind of data were loaded as a result of Caesar execution. So first of all, there are two variables. Each of them is actually array of 26 entries, and alpha is an alphabet, capital letters from A to Z, and gram is array of floating point values that are those floating point values is something called 1 gram table, and it shows how frequently every associated letter in the alphabet is seen in normal English text. There is a whole theory behind the Caesar cipher, actually Caesar cipher breaking, and let me jump to the browser to give you a bit more of a demonstration on this regard. Okay. Okay, I hope you can see my screen, because that was the only way for me to load it. Now a course web page. On the cryptography section, symmetric ciphers, and then Caesar, you can see a PDF file that discusses the general approach to break a CIS cipher. So there is a procedure explained here, and part of this procedure involves using of a 1 gram table. So this is the 1 gram table, as you can see now. So those numbers have just been taken from this table and stored in that Octave, and was stored in that Octave script. Okay, let me figure out. How can I switch back to Okay, something wrong with Hangout session. I cannot go back to share the Octave screen. Okay, let me in this case share the entire screen. This way I can just continue. Can you still see it? Say something, because I cannot see you.
Yeah, I can see it.
Okay.
Yeah, I can see it too.
So I'm currently working on the left bottom corner, and wherever I type, you should be able to see. Okay, we just loaded the CIS script, and there are two variables, alpha and gram, and values of gram here are exactly the ones that you saw and can find in this Caesar PDF file. Now, to tell you more about how the script works, actually, to explain this, let me try to open up the script in the editor, and I will briefly comment a few important parts of the script. First of all, that script is a collection of a number of functions and the two arrays. So the two arrays you're already familiar with. Excuse me. Alpha is defined as array of characters from A to Z, and gram is defined as array of double values. And those functions are, first one is called clean. It is needed to get rid of those characters in a text that do not belong to the alphabet. So in other words, think about some arbitrary text that you just want to encrypt or decrypt. Our alphabet is just a range of letters from A to Z, but there is a great likelihood that there will be small letters, there will be numbers, there will be punctuation marks. So without extending alphabet, our algorithm cannot deal with those extra characters. So what we do, we try to remove everything that doesn't belong to the alphabet. And if something cannot be removed, it is attempted to be uppercased. So in other words, if you just type a word hello, something like hello written from capital H, and then execute this function clean, and it will pass two parameters, the text itself and the alpha, which is this, you're going to experience the way it works. So let me do some illustration. Okay, I'm using a software called tmux. It allows me from the same connection to the server to start two windows. My first window is called Octave, my second window is called VI, and I'm going to jump back and forth to edit the file in one window and to continue execution in another. Currently, I'm in Octave window and I want to execute Octave again, and I'm going to load Caesar script here. Now I will jump to VI editor and will open Caesar script in the editor. So the function clean can be illustrated as follows. I'm going to jump back to Octave, and the way you jump between the windows actually can be tuned up in tmux, but since tmux is pre-installed and you can use it right away with default settings, you want to use Control B and one of those characters to associate particular action. So I'm using next window or previous window to jump between two windows. In other words, what I'm doing is I'm hitting Control plus B, and then I hit either N to jump to the next window or P. So there is a pause after you hit Control B, and then you just hit P or N. You probably might need to watch some tmux tutorial, and that's how it's spelled, tmux. It's called terminal multiplexer. So you can effectively jump between two windows of the same session. Okay, so let me first of all come up with some text, and my text will be hello world, written with mixtured case, and there is a space in between two words, and there are 3 exclamation marks at the end. So I can call a function called clean. That's the function that we just introduced in our file here. And it needs 2 arguments. The first argument it needs is the text itself, and the second argument is alpha, which is our alphabet. So my text is called S, and the alpha is this. A result of execution of this function is hello world, written in capitals. All extra characters are removed, and that's it. I can store result of function execution in a variable as capital. So that is my plain text. Now, what can I do with this plain text? I can encrypt it with the Caesar cipher. And to actually encrypt, I'm going to use a function called CENC, Caesar encryption. What it requires the text, it requires a key. And by the way, if you didn't have a chance to read about Caesar cipher, what it does in terms of encryption, it converts any character, it tries to shift any character to a number of positions to advance or towards the end of the alphabet. For example, if I want to encrypt the word hello, then word hello is considered to have 5 characters, HELLO. Each of these characters can be found in the alphabet, in our alphabet, and each character has a particular position. So let us say I encrypt word hello with the key of 1. In this case, I'm advancing towards end of the alphabet position of every character in one value. So in other words, H will become I. So I is the next character to H, and the distance between H and I is 1. So that's the value of my key. And same will happen to all other characters. If, for example, we are facing a character Z and we want to encrypt it with a key, say, of 2, then we have to consider wrapping around. So with the key of 2, Z will become B. And let us just illustrate the way it works. So Caesar encryptor requires the text, requires the key, and then requires the alphabet itself. And I'm going to use S. Let me just use the key of 0 first. Key of 0 means that I'm not going to shift those letters at all, and in this case no encryption will take place, but execution still will be performed. Since there is no encryption, result of encryption is the same as the plain text. But let me try to use, instead of 0, I will use a key of 1. So H become I, E become F, L become M, L become M, and so on and so forth. With the key of 3, our hello world become Horse Rock, and this is the example illustrated in the PDF file. Okay, so you can just trace that H became K, and the distance between K and H is 3. By the way, one of the ways to see the distance between K and H is 3, except just referring the alphabet, but you can do something like this in Octave. You subtract H from K to get the value of 3. You actually can subtract the entire thing. So, for example, if I store result of encryption in S1, I can, hope I can, yes, I can subtract one string from another to see that it was shifted by 3 positions. Okay? And from this perspective, if you work in Octave, you probably can consider performing encryption in this sense by adding 3 to S. The problem is that it's not going to work right away, because what Octave is trying to do, Octave tries to first of all convert data type of S into numbers, and the way it tries to do it is by means of ASCII table. So in ASCII, sense, every character from A capital to Z capital are assigned with particular numbers. So, for example, A capital is assigned with the code of 65, Z capital will be 90, and they're all located one after another. So when we subtracted H from K, there is no conflict. Excuse me. There is no conflict, because it first converted H in order to respect the subtraction operation to a number, and in this case, code of H would be 72. It then converted K into a number. Corresponding code would be 75, and then it subtracted 72 from 75 to get the value of 3. That's okay. The same way, when we subtracted S from S1, it treated S as array of letters, and then it applied subtraction for each individual letter. That's why we've got array of numbers, and length of this array is exactly the same as length of our array S. But then we try to add value of 3 to S. It looks like it performed well, and actually it performed well because what we see are the ASCII codes of the coarse rock. The problem is that this approach is not reliable, because what if instead of 5, instead of 3, we're going to use some other key, encryption key? One of the values will exceed the highest index that we can operate with, and you remember that the index of Z was 90. So 92 is not a character that we can use, and the character of 92 is actually backslash. So this is not type of encryption that we want. That's why we want to implement a form of wrapping around mechanism, and this is what you can see illustrated in this method. So let me comment how the encryption works, first of all. So encryption assumes that K could be either positive or negative. If it is positive, then it performs positive shift. If it is negative, then it performs negative shift. The way it works, it uses a modular, which is remainder of division of one number to another. And we always divide, we consider division to the length of the alphabet, which is 26. In the PDF file that you will be referring, the length of the alphabet is defined as 26, and they use number 26 in hard-coded manner. In other words, they just don't care that length of the alphabet is different, they hard-code 26. We can see that this alphabet is not good to be used for real text, where a mixture of letters of different cases and numbers and punctuation marks is seen. So we definitely have to extend the alphabet. And that's why our algorithm relies, instead of on number 26, it relies on length of alphabet. So what we do, we first of all try to find index of a letter under study, this index C, in the alphabet, and then we try to manipulate with this. And so, for example, C is iterated through all characters in the given text. And that's how for loops are defined in Octave. Let me do some illustration in this regard. So, for example, if I defined array x from 2 to 6, I can just write a loop and that would be a result of the loop execution. So x is an array, and the loop is executing for each operation. So for each entry in array x, I'm executing the command I. And we know that execution of a command in Octave results in displaying value of that variable. So there are 6 iterations, actually 5 iterations. On each iteration, particular value is extracted, and end4 is a mark of the end of the loop. So this is what we do in a script. We run a C, clean as alpha as an array, and we know that this is an array. It is a result of the previous method execution. So what we do, we access particular character of a given text C, and then we subtract a number that is associated with the very first character stored in the alphabet. In this case, it is A, and we know that numerical representation of A is 65. In this case, what we're trying to do, we're trying to find an index of a letter in the alphabet, index of the letter and the study in the alphabet. So, for example, if my very first character in the given text was A, then it would be 65 minus 65. If it was something else, for example, H, like in our case, A, A, B, C, D, E, F, G, H. So H has the index of 8, A has the index of 1. So 8 minus 1 would be 7, and so on and so forth. The need for the modular arithmetics here in this context is actually to accommodate the wrapping around scheme. So what we do, we let me show you how the parentheses are located here. Okay, it's probably not highlighted, but if you count parentheses, first of all we do the subtraction. Yes, and then we add value of the key, which is positive for encryption or negative for decryption, and then we add length of the alphabet. And it can just be illustrated as follows. So let us say we want to encrypt character H with the key of 3. So to be able to do this, we want to subtract H minus the index of the letter, the first letter in the alphabet, which is 65. I'm sorry, let me just do it without mod. So H minus 65 is 7. And then we add the value of key and the length of the alphabet, which is 26. And then we consider division it by 26. So this operation pretty much is the same as just to add 3 to 7. But with the modular function in use, we are protected to at the higher indices of the alphabet. So in this case, we could just say H minus 65 plus 3, and that's all we need. But let us now consider how encryption would be performed with this expression if we are close to the end of the alphabet. So for example, if we want to encrypt character X, character X has the code of 88, and let's pretend to encrypt it with the code of 10. So it looks like result of encryption is 33. And by the way, 33 is not seen in the alphabet, because in the alphabet we have only 26 characters. We obviously facing out of boundary situation in the array index. So, but if we use our previous approach, instead of H we use X, instead of 3 we use 10. So X becomes 7. And if you look at the alphabet and we'll do the wrapping around, you will see that X becomes 7. So that's how it works. And then we perform the same for every character, and then we just combine all characters, everything to the result, and then we return the result. The breaking part of the algorithm is actually implementation of the technique explained in the PDF file, and I don't really want you to get involved in the way how it is implemented before you actually feel the problem itself. So since this algorithm is just nothing more but implementation of what is already there in PDF file. And your assignment pretty much is focused on you to understand the procedure rather than to learn some specifics of Octave programming. So let me keep it as it is. The only thing that I want to illustrate now is to show that if we use a result of encryption, same as in the example, with the hello world with the key of 3, which is horse rock, and then we apply the breaking algorithm. By the way, breaking algorithm requires the text, which is the ciphertext alphabet, and the 1 gram table. So text, which is S1, alphabet, and the 1 gram table. So our breaking algorithm returns the highest likely result. The highest likely result is 6, and you can see this for this. You can see that the highest likely result was with the key of 6. So we have restored the key same as what was written in the PDF file. They actually have a discussion why this recovered key is incorrect, and it is incorrect because correct key was 3. It is not at the top rank. In brief, the real problem for the inability to decrypt, actually to break the cipher, is because the cipher text is too short. It's not enough good statistics in the cipher text that we can use to break it. So that's why our breaking approach is failed. But if we try to do something else, for example, let's pretend to break this text. Okay. No, not this one. Copy pasting didn't work. So let us try to encrypt this long text, and then we try to break it. So first of all, we want to clean it, and that's the result of the cleaning. As you can see, we converted all small characters into capitals, we removed spaces, etc., etc. And now we do the encryption. So my encryption, let me use key of 7 for encryption. That is the result. And now I'm going to break it. Oh, it recovers correct key. There is no cheating. As you can see, the parameters that we pass into the encryptor and into the breaker algorithm do not involve. So, for example, this number 7 is never listed in the breaking algorithm. It is there, and you will see the way it works. The only trick was that the ciphertext was sufficiently long that the algorithm can pick it up. So now, since we identified the key, we can just use encryptor once again. But instead of S, we will use S1, which is result of encryption. Instead of 7, we can just use C break of S1 alpha and then gram. has to be minused for decryption. And that's exactly the text that we started from here. Okay? As you probably can see that the result of decryption, even though it is the same as was originally there, it is very hard to read because it's only our human being ability to recognize words, but spaces are not there. Capitalized letters are preserved, but lowercase characters have been converted to capitals, and it's not that easy to read this text. So if you will be comfortable in performing all this, and if you will learn Octave in a good way, what you can do, you can make an effort and improve the encryption decryption algorithm. You can do this by, for example, introducing some other function or something else. But what I'm saying is that the first assignment has the extra credit portion, and I would say the extra credit portion is exactly to make result of decryption to have this original nice look. So what you can do for this, you probably want to store original layout of the text where spaces are there, which letters are capital, which letters are small, and then recover this original layout, apply this original layout to the recovered plain text. So that is an extra credit effort, and I suggest you to look at this only if you will learn how Caesar algorithm works. Okay. Any questions? Was it clear? Good. So there are a couple of days, not actually couple, about a week for you to work on this assignment. Should you have something specific, use the discussion board to ask those questions. I will try to answer them. If you will have difficulties in accessing Octave on our LTLSP server, I also will help you out in this situation. Just feel free to use the discussion board for every technical needs and for something that is related to the assignment. But the PDF file with the Caesar is very well written explanatory material, so you can just use it to learn. And of course, Caesar, it's not just explained there. You probably can look around some other sources, but that particular part is very convenient. Okay. Any questions for today? Good. So we'll have another session similar to this that discusses Vigenère cipher, but it's going to be short because for the Vigenère I'm going to post pre-recorded tutorial that I recorded on the previous year. It's pretty much extension to the Caesar, and the only need for the live tutorial session would be for you to be able to ask questions, if any. But that will be after you will complete the Caesar. And we also will have a third tutorial live session for the lab practice, where I will be just demonstrating some web sniffing techniques that you will be asked to do in the lab. So I hope you enjoy this format, and just feel free to ask questions if any. All right, that's it for today. I'm going to stop the recording at this point, and thank you for watching.